that's what we're going to cover today. It's how did we put this together? What does it mean? What are we studying? What? Okay. So if there's no questions, I will get started. I'm not going to go through the population and parameter and statistic and all that. I'm just going to jump right into this. Okay. I'm going to say this as well. Come next week, probably Tuesday, we're going to do a lecture that's going to be on regression. And this one is the one that is going to get you. As soon as we do the regression one is when you get hooked. That's when you realize this is why we're taking the class. That's a lecture that makes this whole statistics stuff make sense. Why? And after that, you're never going to be the same. Right? It's like eating your first ice cream. After that, or a cookie or something, right? You'll never be able to look at stuff the same once we cross that boundary. Again, I said at the very beginning that all of a sudden you're going to hit a crash. As soon as we get into regression, you will crash for sure. I just want to make sure that I'm clear about that. And when you start to crash, don't feel, woe is me, oh my God, I'm stupid, everybody told me I can't do this. Don't do that. But I'm telling you, it's completely normal. I've been doing this for a lot of years. The best way that somebody put it to me is cry a river, build a bridge, and we'll get over it together. But we're definitely going to get through this. What happens? Take you to your absolute capacity of what you can do till your mind crashes. You can't do anymore. We'll build you up, get you to that point, dust you off, pick you up, and get you moving forward beyond what your capacity used to be. Okay? And that's the reason why you crash. So start building this complex neural network. But don't worry, I've been doing this stuff for about 20 years. We're going to be fine. Okay? Just to let you know. Best thing to do is get a gallon of ice cream, go home, yell at the boyfriend or the girlfriend, kick the dog, eat the ice cream, maybe some cookies too, and we'll be fine. Okay? A couple days later, you'll be like, okay, it's not so bad. So let's move forward. So now what I'm going to do is I am going to go back to this ANOVA. Okay, let's take a look at this ANOVA, at this golf ball example, and make sense of it again. Seems like the net's running a little bit slow today. Okay. So always, whenever we're studying things, you always want to say what the hell it is that you're doing. You just don't want to all of a sudden put something to someone and say, please no, reject it all. The hell do you want? What are you kind of studying? What are you looking at? What are you trying to figure out here? Whenever we're trying to make decisions, what we try to do is to get as much information as we can, form it together where it makes sense, and how we want to question and answer this thing in order to answer stuff. And we do this all day. When you're driving, you're like, should I go down this road or should I go down that road? You want to get more information, you turn on to the radio or the news channel and check out the flow of the traffic, and then you make a decision based off of that. So what we try to do always before we make a decision, get as much information as we can, and then weigh our decision. And that's what we're doing here. This is called decision sciences. That's what typically statistics is. It's under. And then a guy's name is Sherlock Holmes. And Sherlock Holmes once said, it's a capital mistake to make a decision. So what we're going to try to do is to get all the information, kind of organize it, like, what does this mean? In this case, what we're trying to do is we have a golf company and we make golf balls. And which golf ball do we sell? And you're thinking like, well, I don't know, which one looks best? No, what we're going to do is we're going to look at the performance of them. Based off of the performance of our product, that's the one that we're going to sell. Okay? And so we have a couple different designs. We're making it out of different compositions. And so which one goes? So here's the problem. You have golf ball 1, 2, 3, and 4. Every every time you hit that golf ball, does it go the same distance? No. Maybe one time it goes 150 yards, the next time it goes 300 yards. One time it goes 280, whatever. But it doesn't go the same amount. So you have to find out what's the average distance that each golf ball goes, each design, each different composition. And so those average distances are known as means. So what we can do is see what is the mean for each golf ball. And maybe this one is 240 yards, this one is 235 yards, this is 210, this is 240 yards. I just made those numbers, pulled it out of the sky, okay? And we want to compare them. Is it just normal variability? Because maybe this one sometimes I hit 150 yards, and maybe this one sometimes goes way more than 150 yards. Normal variability, or is one of them statistically significantly different? So we take all this data, we crunch it all the way together, we create this confidence interval, and based on the confidence interval, what we want to see is one statistically significantly different. Because we're not hitting this golf ball for the entire life of this golf ball, and we're not hitting every single golf ball that we produce and test every single one and then give it to somebody, because as you're testing it, you're using it for perhaps the performance is going down every time you use it. So we're going to do a sample, and sample set variability. So we need, just because the number's higher doesn't mean that it outperforms another one, because we have to deal with variability. Right? Perhaps we take this golf ball and we hit it one time and it goes, because 204 is the average, but maybe we hit it one time and it goes 255 yards. And we hit this for the first time, and perhaps this goes 180 yards. And we could mistakenly say, oh, wait a minute, this one's better. No. What we need to do is to get an average and then look at variability and see where that thing ends up. And so what we're trying to do is to compare these. But you don't just want to all of a sudden look at golf ball data, compare the designs of the golf balls, and then when somebody says, hey, so what do you think about the golf balls? You know, you're at a meeting, you're like, P is low, reject the null. What are you talking about? Maybe the people that are in the accounting department have no clue what you're talking about. Maybe the people that are in operations, what are you talking about? Reject the null hypothesis. What you want to do is to clearly state what you're doing and what has taken place. What you would say is, you know what? What we tried to do was to test all 4 golf balls. After testing all 4 golf balls, we hypothesized that all the golf balls would be the same. But you know what? We were wrong. Actually, one of the golf balls, at least one of them, outperforms the rest. We were able to determine this by comparing the averages against each other. And from those averages, we were actually calculating what's the probability that one will outperform another one. And so we'd be able to say that with that, after we figured out that one of them was different because the probability value was lower level significance, we're able to determine using something called the Zucchi-Kramer which one was the best. And at that point, we can say, you know what, we found out that golf ball 4 is actually the best. Then we want to say, then somebody would say, well, how do you know that your test is accurate? I mean, is your test good or, you know? So we'd also want to cover that. But wait a minute, we want to check to make sure that the test that we actually used to determine this was reliable. And so the way that we check our reliability in the ANOVA is we have a couple of assumptions. One is called independence, normality, and equal variances. And why do we check these 3 things? So one, we want to state what it is that we're doing, what the results are, and then we want to make sure that we tell them, hey, wait a minute. I myself was skeptical of the results that I got, so what I needed to do was to validate my results, right? And so that gives a little bit more comfort to see where we're at. So what is independence, normality, and equal variance? Okay, so right now we're able to determine that one of the golf balls is different, and in our case, we determined that golf ball design 3, I think, was statistically significantly different than all the rest, right? And so now let's look at this idea of independence, normality, equal variances, and what that actually means. So I have these little stories that I'd love to share. And so sometimes I'll have these stories that sometimes I have these little stories that they're very difficult concept to understand. And I have these funny little anecdotes or stories or whatever to help your mind process this. So this is one of those ones that I need you to pay attention to, or you need you to pay attention to, because if you don't, you're going to get stuck. And it's going to be a funny story. You're going to laugh. Oh my God, Chris, you're not. That's cool. So I have a brother, Patrick, and Pat is thinking about starting an automotive business to put brake pads on cars. And so what he's planning on doing is he wants to be able to tell the customers which brake pads are best. Somebody comes in and says, hey, what do you recommend? Garrison comes in, hey, I just got a brand new Ferrari. We'll put some brake pads on it. It's not new, it's a little bit old, that's why I need brake pads. But which ones do you recommend? And so he wants to test them to see which ones actually work better. He doesn't care what's written on the package. He wants to actually test them. And so what he does is he designs his own test. And so what he wants to do is he has 4 different brake pads that he's thinking about carrying at his company. One is called Bosch. One is called Tokiko, Delco, and the infamous Walmart brake pad. So Walmart actually has their own brand. And so my brother, he's not exactly the sharpest tool in the shed, right? My brother Pat's always trying to take shortcuts. He's always trying to. So what he decides to do is he's going to take a car and he's going to drive it up to like 50 miles an hour, hold it at 50 miles an hour, and get to this line and then put on the brakes to see where the brake, how far they go. So what he tries to do, just to save time, is he puts brake pad number 1 right here, brake pad number 2 right there, brake pad 3 there, and brake pad 4 there, all on the car at the same time. He's like, I'm going to save time, so I'll put brake pad here, 1. So Bosch brake pad there, Tokiko here, Delco there, and Walmart brand there, all at the same time. So he gets in the car, he gets it up to 50 miles an hour, holds it at 50, puts on the brake, and he stops at 199 feet. And he says, okay, that time will be for brake pad number 1. He gets in the same car set up the exact same way, gets up to 50 miles an hour, holds it, puts on the brakes, 201 feet. He says, oh, that's for brake pad number 2. The car is set up the exact same way, gets in it, goes up to 50 miles an hour, puts on the brakes, stops 198 feet. That's for brake pad number 3. Wow, that's pretty good. Actually, it looks like brake pad number 3, Delco, is performing the best here. Gets in the car the last time, puts on the brakes, goes 202 feet. He says that's for brake pad number 4. Anyone can see that brake pad number 3 is the best. Isn't that right, Edna? Can we test it like this, Edna? Edna, are you there?
Probably not, because there's definitely other factors to go in with it.
Well, why can't we test it like this? Are we not independently checking this? Are all these kind of tied together? Perhaps that's what the deal is. Perhaps we need to independently check things. And sometimes when we have things that are kind of tied together, we're not independently checking things. The results are wrong. Honestly, this car should stop at the same distance every time. Every time it should stop at the same distance. The reason why it's not stopping at the same distance is because of error. It's either random error or systematic error, right? It's the reason why it's not stopping the same distance is either because of random or systematic error, but it should be stopping the same distance every time. These results are not valid because we're not independently checking things. These things are not independently being checked. And so we have some issues. Okay. So when things are not independent, the reason for the differences is error. Right? It's either systematic or random error. Questions on this? So one thing, favor please. You ever see me walking in the mall and I'm walking with my brother Patrick? Do not tell him, hey, your brother uses you for an example in class. He's got anger management problems, okay? He just didn't go there. So that's me. Okay. So let's now move on. So independence, we need to make sure that things are independent. How do we do that? Random sample. A random sample is also known as a probability sample. So if it's not random, you really can't get probabilities from it. Okay? So we need to have a random sample. Later on, this is going to come up in something known as regression. We're going to be looking at the Durbin-Watson. And then all of a sudden, we're going to find out, hey, wait a minute, we have found correlation problems. What does that mean? That means we have issues with that standard error or error. Okay? So we're going to look at this a little bit later on. So just make sure that we keep this in mind. Okay? Independence. Normality. We know that already. That's skewness and kurtosis. What does normality tell us? So our skewness and kurtosis has to be between -1 and 1. We can also look at a box of whisker to see if it's normal. We can also look at something else in normal probability. But skewness and kurtosis, if it's not normal, that means it's not representative or it's not what we would normally find in the normal population. It also means that we could have outliers, and it also means that probability is no good. So for our test, because we're using the probability, the p-value being below the level of significance to reject a null hypothesis, we need to make sure that probability is accurate. And if skewness and kurtosis is not between -1 and 1, guess what? Probability is probability. I'm going to focus on this for a second. Okay. Right up here, IND, independence, normality, and equivariance. So I have another example because I want to drill this in your head. I want you to be able to see what I'm talking about in your head. And when somebody talks to you and they start describing something, you'll actually be able to see it and understand it, not just as theoretical mumbo jumbo. I like theoretical stuff, but we're going to go past that. You with me here, Lisa? Okay. So, let me see who I can use for that. Can I use it for example, Blaze? Blaze?
Yeah, sure.
So, it's been a rough semester. And so Blaze needs to blow off a little bit of steam. Just got to a party, right? Blaze lives in the dorms. I'm just making this up. I know the dorms are closed, but Blaze lives in the dorms. He's going to a party. Dorms are now, are they dry now? I think they're dry. And I think dry means like no alcohol. I believe that. I don't know if that's actually true. I still imagine there's some flip cup card parties going on. But so Blaze decides to throw a party. And so Rose is going to come to the party. And so she's thinking, okay, what do I bring to a party at the dorms? And you know, she likes to bake stuff in the oven because I know baking has a couple different meanings here. So Rose likes to bake, and so she's going to make some brownies for the party, right? And so Rose has a roommate, and roommates always stay. You always take your food, wear your clothes, all that type of stuff. But so Rose is going to make these brownies, and she got these beautiful mixing cups at Ross. Unfortunately, they're made out of plastic, but they're beautiful looking cups. And she puts them out on her stove the nighttime before because she can wake up in the morning and make these brownies fresh for the next day. Because she's got this party to go to at the dorms, right? And I know brownies are a big hit. So in the morning time, her roommate wakes up and starts cooking some stuff. Doesn't move her mixing cups. And the mixing cups actually get all the fingers. I mean, they're cooking her food even. And when she wakes up in the morning, one mixing cup looks like that. You know, the other mixing cup is like that. One mixing cup is like that. And another mixing cup is how it got like that. I have no idea. But one mixing cup is like that, right? And so this concept right here, I just want you to understand it. Even though it's funny or whatever, it's honestly like, it's going to be one of those things that if you get it, it's going to make sense. It'll actually enhance your understanding of what we're looking at. So here we are, we're going to make these brownies, right? And so Elisa's been to a few parties at the dorm, and so she knows how to make these brownies. And so what goes into this? Like 2 cups of
flour, sugar, chocolate, butter, oil.
Flour, and 3 cups of chocolate chips. And Elisa has this spice that she puts in it. I don't know, but she has like 2 cups of some type of spice. And a cup of eggs. You can tell I can't bake here, right? Is this going to turn out right, Rose? What do you think?
Probably not because of the proportions.
Okay. So the device that we're using to measure is inaccurate. And therefore, the end result is going to be inaccurate. Is that what we're saying?
Yes.
Okay. Not consistent either, right? But how about if it wasn't 2 cups of flour, but 2 grains? And instead of 3 cups of chocolate chip, 3 grains of chocolate chip. And then instead of the 2 cups of Elisa spice, you only need 2 grains of whatever that spice is. And instead of 1 cup of eggs, we need 1 grain of eggs. It's going to be a hell of a small brownie. I get it. Would it work?
No, maybe no.
You don't think so? Would the shape of the device using to measure have an effect on it? If the amount that we're using is really small, would it affect it? What do you think, Lisa?
Like if it still measures the same amount, but it's a different shape, then no, I don't think so. But I guess it might just make the measurement process more involved or complicated.
What do you think, Carson? Carson, sorry.
Yeah.
So so this is what the key is here. The measurement is so small that the inaccuracies or the shape of the data, even though that it's inaccurate, the device that you're using is not accurate. The measurement is so small that it does not affect our end results at all. And so this idea helps us with this concept. And this concept, a lot of people have a hard time wrapping their heads around. If our skewness and kurtosis is not between -1 to 1, then the p-value is inaccurate. So the device that we're using to measure is inaccurate. Now imagine if we have an extremely small p-value. If our p-value is extremely small, even though the device that we're using, the bell-shaped curve, is off, even though the shape of that curve is off, because the measurement is extremely small, they're using. Right? I understand that it's not going to be accurate. But the measurement's extremely small, so it'd be okay, which tells us this. Even though, so if we had a skewness and kurtosis of 4.2 and negative 3.8, we know that our p-value is inaccurate because our data is skewed. But even though with these inaccuracies, instead of using our p-value, when we start to see how inaccurate, what does a skewness of 4.2 do to us? What does that do to us? So remember, before we had this. 34%, 34, 13, 13, 2, and 2. So 5, 4, 2, and 0. If we were to do this, 12, 4, 47, 46, 13. Here we have the data skewed, right? We're actually missing this stuff. We're missing these portions. So our data is actually skewed. We're missing this. When we look at our probabilities, this tells us that 34% of the people should jump from 4 to 6 feet, 34% from 6 to 8 feet, from 2 to 4 feet, 13%, from 0 to 2 feet, 2%. The probability somebody would jump less than 4 feet, we can figure that with the z-score, is about 15%. 13 plus 2. So when our data is skewed, our data is pushed this way and skewed, guess what? When we look at that probability, it should be that 15% of the people jump less than 4 feet. And guess what ours is? We have no data there. Because our data is skewed, the probability is low. So when we're looking at something like this, how far off is it? How far off would we be with the skewness and kurtosis of this? And we're looking at less than 2%. Something like this would be off by maybe 1%. So a good rule of thumb when we're looking at this is how far off is it? So what I like to do is so right here we're looking at maybe 1%. If we have skewness and kurtosis of maybe about 8 or 9, we're looking at maybe about 7%. 7%. So skewness or kurtosis of 9, we're off by roughly 7%. Maybe skewness or kurtosis of 12, maybe off by about 10%. So if we had a skewness and kurtosis of 12, and it's off by 10%, I want you to be able to see this. Negative or positive. And it's off by 10%. And if our level of significance is 0.5, and we know that this p-value is not accurate, it's off by 10%. We want to be able to reject or null. So even if it's off by 10%, watch this. Is that still below 0.5? Somebody help me. Is that still below 0.5, Jamon? Yeah. Even if it's below 10%, we're still able to reject or null. I just want you to kind of see that. I want you to be able to see that. Okay? So I understand that we want our skewness and kurtosis between that for normality, but even if the data is not normal, if our p-value is low enough, we're still able to reject our null hypothesis. Okay? Equal variances. What does that mean? I'm going into this NOVA kind of a little bit deep for 2 reasons. One, because it's a major component of the progression. That's what we need to understand. So we need to build upon this. I need to make sure it's in your head. Okay? So what does equal variance mean? So here we have two golf balls. Okay. And when we're looking at these two golf balls, you with me here, Jacob? So we're looking at these two golf balls, Jacob. And so one of them goes 250 feet, the other one goes 199. Is that enough information to say which one's better, or do we need more information?
You would need more information.
Remember I said that sometimes at the beginning of class, when you ask me a question, instead of just telling you yes or no, I'll answer it with a question. Now you're doing that to me. That's okay, because I got more information for you. So on average, this goes 250 yards. On average, mean that goes 199 yards. This has a standard deviation of 50 yards, and this has a standard deviation of 1 yard. Which golf ball better now?
The 199 one, because it varies less.
So you hit this one, and it could go 201 feet, or it could go 198 feet. This one right here, you hit it, it could go 300 yards, or it could go 200 yards. Right? Which is scary. Right?
Wouldn't you use the 251 then?
Well, so see
Because
this-
it would always go pretty much more than 200.
okay. That's more.
Like, do we gauge what's better by which one's more precise? Because yeah, I was thinking the same thing as Jacob. Like, even at its worst, the 250 would still go the same as the other one could at its best.
So here's the interesting thing. Imagine you're playing golf and you go to hit the ball and the hole's 1 yard away. It goes 50 yards. You really want to use that ball?
Probably not.
Just saying. But there are times where this ball right here outperforms that one. And there's times where it's even. Do we see that?
Yeah.
And so we wouldn't be able to say that it always goes higher because there's sometimes when it doesn't. Right? There's sometimes when it doesn't. And this one, when you look at it, is 51 yards more than that one. But there are times that this one does not outperform this one. But there's times where they're actually even. And so what we want to do is we want to make sure that this one always outperforms that one. That there aren't times when they're the same. So what do we look at? We want to make sure that these things, the things that we're testing, both have the same consistency, right? And so what we're going to look at is our standard deviations, just to make sure that they always are the same. So imagine if this one was off by 100 yards, 150 yards. Let's do 100 yards just to make things interesting. So at times, this would go 150 yards or 350 yards. Can you see that? See this one right here? There are quite a bit of times that this one outperforms that one if we were to use 100 yards standard deviation. So what we need to do, so if we look at the number, it would tell us, oh no, the mean is higher. And then if we were to automatically just say, okay, because this mean is higher than that one, it's statistically significantly different. What we need to do is to make sure that it's consistently higher. And that's what we're going to do with our equal variances. We want to make sure that one standard deviation is not double the value of another one. So we have something known as the 2 times rule. Equal variances, it's called the 2 times rule. The lowest standard deviation cannot be half the value of the higher one. Or the highest standard deviation cannot have double the value of the lowest one. Meaning this, if one standard deviation is 2, the highest cannot be more than 4. If a standard deviation is 10, the other one can't be higher than 20. If one of them is 50, the other one can't be higher than 100. Double the value, 2 times rule, right? And so what this is measuring is to make sure that the mean is consistently higher than the other mean. This one right here is checking the p-value, and this one right here is checking to make sure that we don't have errors. And really, if it's not a random sample, the results could be just due to error. And so those are the assumptions that we're looking at with our ANOVA. We have questions about that? Those are some pretty heavy concepts that I have these little stories to kind of back. But do we have any questions about that particular thing? Any of that? So let me do our, I'm going to do our PowerPoint presentation. After I do the PowerPoint presentation, we're going to go back to, our golf ball example and back to homework. Because I want to make sure I give us some theoretical background here too now. Because otherwise we will be stuck. I'm not sure if it's lecture 10 or 11. Hang on, let me open this up. Okay. Now let me share my screen. Can we see this, Natalie? Okay. So today we're going to look at our 2 sample tests. This is 2 or more, and it's called one-way ANOVA. Analysis of variance is what ANOVA stands for. It was also called the F test, but the F word got a bad name during the 70s, so they stopped calling it the F test. The reason why it was called the F test, it was named after a guy named Fisher. And so Fisher's the guy that did that, so we call it the Fisher test as well. And so in this chapter, we'll learn hypothesis testing procedure for 2 independent populations, right? The means of 2 or more populations. So here we have 2 sample tests, right? Independent samples, they have to be independent. Remember we said that earlier, because if they're not, the differences are caused by error, either random or systematic. One of the tests is the ANOVA. See right there, it says F test. F test is the same thing. The ANOVA only tells us one of them is different. It does not say which one's different, which stinks. It doesn't say this one's different. All it says is one of them's different, right? If we're looking at our golf ball example, all it says, we have 4 different golf balls here, and it says, okay, one's different. You're like, well, wouldn't it be nice to know which one's different? In order to find out which one's different, we have a test called post hoc, and that is known as, the one that we use is the Tukey-Kramer. In your marketing classes, you're going to use the Duncan, but once you learn the Tukey-Kramer, you'll be able to read the Duncan. Okay, so multiple sample tests, we can test all kinds of things. Remember that I want this to be in your head, is when you're testing things, all you're doing is trying to find out if there's differences between the things that you're testing. That's all these tests tell you. Is one number higher than another? Is one mean higher than another? Is one marketing plan better than another one? Does it give us more sales? Does one mutual fund or one investment package give us more money consistently? Is one stock consistently higher than another stock? Right? Is one safety program higher than another safety program? Does this new machine that we're buying, does it produce more than the old machine? Is it more efficient? Does it use less electricity? We're not just going to measure one day and say, okay, this is good. No, we'll measure a few days and actually tabulate it to see if it does. If you have a company and you want to find out which shoes which computer, which car, whatever it is that you're selling, should I sell in Alabama or Florida or California? There are tests that we can test the market to see which one is the best application. And all it tells us is, yeah, this product is significantly different than the rest. We have a higher amount for selling in Texas, so Florida. And that would tell us which one to sell where. But again, the test just tells us if one of them are different than the other one. That's it. Don't try to make the test do something that it doesn't do. We're comparing means to each other, and what all we're seeing is one mean higher or was one mean lower than the rest. But all it tells us is some of them are different. Right? So I want to make sure that I get you to understand that. So a hotel bar introduced late night happy hour promotion to see if they can increase revenue during the slow period from 11 o'clock to 12. You want to see if the promotions are successful. So we have the data, and with this data, we can actually start to begin to test things, right? We're looking at this, and we can say, okay, wait a minute, let's test to see what's the average amount of money that we made before the happy hour, and what's the average amount of money that we made after the happy hour. And then we can begin to test, like, does it make sense to keep it, right? Because we're giving away free food and stuff. And so what we have to remember is different days give us different amount of people that show up there. And it could be that just randomly somebody's having a birthday party or a football game or whatever. And we want to make sure that when we're testing these things, that this is a normal time period. And that's why we also want to check the shape of our data. If we're checking to see does happy hour work on Monday nights during football season, yes. But maybe that Monday night after football season's done, hockey's done, it's just a regular Monday night and it's a dead cold of winter and just nothing going on. People don't want to leave their house at 4 below zero in Minneapolis. Perhaps we can't apply that data to that. So we got to make sure that we're looking at the big picture here. So we want to test our means against each other, right? We can have categorical, we can have numerical, right? So categorical, numerical. Numerical, we're going to use our ANOVA. Categorical, we're going to use our chi-square, but we can also use a dummy variable too in ANOVA. Okay. So again, the goal is to see if there is a difference between the means. What we're trying to do is to figure out if one sample is actually greater than another. Whatever it is that we're testing. Is this marketing plan better than another one? And the only thing that the ANOVA will tell us is if one mean is higher than another. That's it. We want to make sure that our samples are independent. Unrelated. We get our data from a different sample set. So I'm going to say this just to say it because I need to make sure that we understand this concept. When I say independent, there's no such thing as fully independent, and I need us to wrap our head around that. When my brother was testing the car, and we needed to make sure that we had different brake pads all at the same time on the car. We wanted to make sure that it wasn't dependent, that we had different brake pads. Right? We want to make sure that one time we're testing the Bosch, one time Delco, another time the Tokiko, another time the Walmart. We want to make sure that it's independent, but there are some things that are dependent. What? So, don't we want to use the same car? We don't want to check the Bosch on a Porsche and then check the Delco on Grandma's minivan. No. We're going to get some different results here. So some things are kind of dependent, right? That we want to make sure that we include in that, right? We want to use the same minivan or the same car every time. We don't want to test one in perfect condition and the other one in snow. No. So there are some things that we want to make sure that are the same. We don't want to test one on a hill and the other one on flat ground. No. And so some things are independent, but some things have to be consistently the same, right? So I just want to make sure that we're clear about that, because when we get to regression, We're going to look at autocorrelation. You're going to say, well, how come it's not zero? How come it's not no thing? And I'm like, well, you can't just independently check something without other things that are affecting it. So we just need to make sure that we keep that in our mind, okay? So some things are not going to be fully independent. Okay, can we see that, Lauren? Give me a thumbs up. Okay. So we're looking at this, and we want to make sure that some things are independent, right? Independent. And when we, so independent, and the way that we get an independence, at least in the ANOVA, is a random sample. A random sample is also called a probability sample. Okay, so a random sample. Another assumption is equal variances. Equal variances, right? And what we say assumption is this. When we reject our null hypothesis, and we're saying that, oh, they're different, we're assuming, we are counting on that we have equal variances, that they equal about the same. We're also assuming that our p-value is accurate, and we're assuming that our samples are independent. So our assumptions, right? And so we need to make sure for that, to make sure that our test is actually valid and reliable. That way, when we tell somebody, yeah, golf ball 4 is the best, or 3, we're able to validate that. Okay? So again, after we run the test, we want to use our Tukey-Kramer. And so we can evaluate things like accident rates for first, second, and third shift, expected mileage for different tire brands. They do that all the time, right? So here's one that I think that you guys will find particularly interesting. I'll just spend a moment on it, and I should have the article on it to show you. But so they believe, this is my conspiracy theory side coming out, just for a second. Let us back my data. So they believe that this COVID virus was created in the lab, and that somebody engineered it. And so what's absolutely weird is that they notice that there's these patterns of things, right? So they start looking at people, and as they're looking at people, they start looking at DNA and blood types. And wouldn't you know, they're looking at A, B, O, and I think the other ones are AB. And they find out that blood type A, because they ran these ANOVAs to see who's actually catching this COVID. Blood type A people are statistically significantly higher amounts catch COVID than any of the rest of them. And O is the least. And when they looked at the sample of the people in the cities that were catching it, they went to Wuhan, they went to all these, a bunch of other cities. And so if you type in the internet, an analysis of variance, ANOVA test to test blood type and COVID, because they're doing a lot of research on it right now. They find out that in the cities, the largest population in the cities are type O, but they're not catching the COVID. But the ones that are at a very high rate is A. And the sad thing is the people that have the blood type A, when you catch it, you get much more sick than some of the other blood types. And so it's interesting. So the ANOVA, they're actually using this to test it right now for this thing that we're looking at. And go online and you'll see all this research right now. But they're using it. And so the ANOVA is now told us that there's statistically significantly different on the amount of COVID cases based upon blood type. And they found out that the one that's statistically significantly higher blood type A. Blood type O B and AB are in here. Okay? So we're just kind of looking at that. Just want to make sure that. And so that's some research that they're actually doing right now with this ANOVA that they're applying to it. So we're not learning something that's just in the wrong. Let's go back to this. See if we can get through this. Okay. Max. So the way that you write up a hypothesis, and those of you who are doing homework, remember I said that I'm going to lecture on things, and after I lecture on it, I should give you enough information that would allow you to do homework. So this is how you write up a hypothesis for the ANOVA. You can either go like this, all populations are equal, no treatment effect. You can also write all the 4 golf balls will go the same distance. Not all the population means are the same. At least one golf ball will be different. At least one population mean will be different. There's no treatment in effect. And you can write it up any of those ways. When we test it, this is what we're looking at. We have the 3 means that are here, and then we're going to create a confidence interval for all of them. And then based off of that, we're going to be able to compare to see if one of them is statistically significantly different. Here's the one that we're actually working on right now, is actually in our PowerPoint slides. So you want to see if different, this is looking at golf clubs as opposed to golf balls. So we're looking at club 1, 2, and 3, and we hit different distances. And let's see now which one outperforms which one. Okay, so here we have the distances. We can then write up a hypothesis for the golf clubs. Golf club 1, 2, and 3 are all the same. At least one of the golf clubs will outperform the other ones. Okay. Now we look at them and we find out that the mean for golf club 1 is 249, the mean is 226, and this is 205. But is that statistically significantly different? Or is it just normal variability? Right? And so we can actually check that. We run an ANOVA. Here's the amount of times that we tested it, 5 times. These are our sums. That's our means. Those are our average. Golf club 1, 249. Golf club 2, 226. Golf club 3, 205. That's our variance. If I take this number, square rooted, I get my standard deviation. This is our sum of squares, our degrees of freedom, 3 groups minus 2. That mean of squares is that number divided by that number divided by that number. That gives us F critical, and that's our p-value. So if our p-value is below a level of significance, we can reject our null. So we said at least one of them is different. That p-value is below 0.5. We can reject our null hypothesis and say one golf club is statistically significantly different. Right? Now, how do we know which one's different? Right? How do we know which one's different? We have to use our Tukey-Kramer. Right? We also want to check our assumptions. So we're looking at our skewness and kurtosis. Do we see those numbers right there? That tells me, one, that our skewness, that our p-value is inaccurate. But our p-value is extremely low. So we're off by less than 1%. Okay. So our p-value is inaccurate, but it's extremely low. We also want to look at our standard deviations. The lowest can't be double the value of the highest. So our lowest standard deviation is 8, so our highest can't be any higher than 16. So this is okay. But there's also another rule that if we have the same sample size, the same count, if we have the same count, then equal variances is assumed. Also, if our, if we have the same count. Also, if our count is above 30, then it's assumed to be normally distributed. Okay. So it will tell us which one is significantly different, After that, we're going to look at our Tukey-Kramer. This is how you calculate the Tukey-Kramer. Are we going to calculate this? No. Our computer will do it for us. We find our Q statistic in the back of our book. Then our Tukey-Kramer will tell us which means are different than other means, right? So we'll be able to tell which one's significantly better. So far, so good. That's our chapter summary. Now let's get to homework again. I timed it perfectly because I wanted to make sure that we had at least about a half an hour to do homework, okay? So let's now go back to homework, okay? So again, we had our golf balls. We looked at our distances. We ran our ANOVA. We wrote up our hypothesis. Our level of significance was 0.05. Our p-value was point and then what, 16 zeros? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 5. You know, I know what a million is. I know what a billion is. I know what a trillion is. I know what 10 trillion is, 100 trillion, a million trillion. I don't know what comes after a trillion. I used to. And then whatever comes after a trillion, whatever comes after that is the number that we have. So that number is extremely small. So there is significant evidence to reject our null. I'm almost 100% confident that one of the golf clubs is different. Which one? I don't know. The way that we tell, that's all the ANOVA tells us. The way that we tell is we look at our Tukey-Kramer. When we look at our Tukey-Kramer, we wrote a number line, and we were able to determine with our number line that golf club number 3 was statistically significantly, or golf ball number 3, sorry, was statistically significantly better than the rest. Now, what we wanted to do after that is we needed to also make sure that our, can you guys see my screen?
No.
Damn it. I'm glad I asked that question. Okay. Can you see it now? Okay. So here again, we have our golf balls. I wrote our hypothesis and our alternative hypothesis. Then we have our p-value right here and our level of significance. And because our p-value is below our level of significance, we can now reject our null. There's sufficient evidence to reject our null, and I'm 100% confident that one of these golf balls outproduces the rest. Which golf ball produces the rest? I don't know, because the ANOVA doesn't tell us that. If we want to find out which one's different, we have to use our Tukey-Kramer. Okay? So now I'm going to go to our Tukey-Kramer, and when we ran our Tukey-Kramer, we found out that golf ball number 3 outperformed all the rest. The one that was in second place was golf ball 2, followed by golf ball 1, followed by golf ball 4, because we did our number line. So now that we have tested this, we want to make sure, we want to validate this test. How do we validate it? We need to make sure that our descriptive statistics is okay. We need to make sure that it's independence, normality, and equal variances. Independence is a random test. So we're going to say that it's a random test. So independence is okay. Normality, we're going to check our skewness and kurtosis. How do we do that? We run our descriptive statistics. can run it in PHStat. And so how do we make sure that our p-value is accurate? We look at our skewness or kurtosis. But in all honesty, our p-value is so low that even if our skewness and kurtosis was off, we'd still reject our null. See this right here? It's okay. Our p-value is accurate. Now let's check our equal variances. We have our 2 times rule. So the lowest value and the highest value cannot be double the value apart. Our lowest value is 1. So our highest value 1.1. So our highest value can't be any higher than 2.2. Right? Do you remember what I said, Russ? What's another way of looking at it where it doesn't affect us? How can we get around the 2 times rule? Do you remember?
I do not remember.
It's okay. Because somebody's here to teach it to you. So the way that this works, again, is that if our sample size is the exact same size, then equal variances is assumed. You see that, Mia? If our sample sizes are the same, then equal variances is assumed. Are our sample sizes the same? Microphone's still not working. Okay. So we have the same count, so it's assumed. So now let's write this up. Okay, how do we write this up? So I am going to get, we actually have our template, and we are going to use our template to write this up. Okay. And after we do that, then we're going to go to our next one, our bond fund, and we'll answer that last question. Right? And I'm going to show you guys how to write this up. We're also looking at our aims too. The aims is a file that I think we're comparing means as well, but we'll take a look at that. We'll run that as well. And then we'll go to our chi-square. I'm waiting for this document to load, so I apologize. I have to share one screen, kill it, and then go back to see if it'll share the other screen. I don't know why. See if it works now. Okay. Can you see that, Nora? Okay. So now let's change this ANOVA to work for us. Sorry, I know that's smaller. Not all means are equal. It was hypothesized because what we want to do is we want to clearly tell people what it is we're testing and what took place, not just the p is low, so I rejected the null. But what does that mean? What are you testing? What's different? It was hypothesized that the 4 golf balls would PERFORM perform the same? In order to test this hypothesis, an analysis of variance was utilized. It was found to be statistically significant. There's sufficient evidence to reject the null hypothesis that the Gulf Falls Can you guys see this? Yep, I got a thumbs up already. Equal or the same. You could use either word. The level of significance was 0.05. The p-value was, oh my God, it was 16 zeros and then a 5. I'm just going to write 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 5. I know I can put in more, but, and you can put in all 15. I'm going to put 100% confident that the performance of the Gulf Falls is not equal. The sample size in our case was 10. So it's not surpassing the central limit theorem. And I haven't showed you the video on that yet. But what the simple central limit theorem proposes is that if the sample size is greater than 30, and so we're looking at 30 means, then it's assumed to be equally variable, even if the skewness of kurtosis is off. Right? It's assumed to be equally variable. So we're going to put not surpassing the central limit theorem requirements of 30. So we then checked our skewness and kurtosis to validate the p-value. Skewness and kurtosis was you can write in range or between -1 to 1. The assumption of equal variances was met because the sample sizes were equal, or right the same at or in there 10. The Tukey-Kramer procedure indicates, which one was it? Was it Gulf Ball number 3? Somebody help me here. Wilfred, which golf ball produced the best? Do you remember? How about you, Rose? Which golf ball went the farthest?
I don't remember.
The what?
I don't remember.
I think it's golf ball number 3. Outperform the rest. Okay. And that would be our ANOVA in a nutshell. That's how you can write it up. Okay. And what we did was we tested it to see which golf ball performed the best. Doesn't have to be golf balls. We could test anything. Okay. So far, so good. Questions on this? Somebody can ask me. So you would just copy this and you could paste this, and I would answer all the questions for the ANOVA on that. I think in the homework we also had AMS file, AIMS file. And so looking at our AIMS file, let me share this with you guys. Here we have an email system, or we have computer systems, and we're looking at like emails or refresh rates and stuff like that. And we're comparing system 1, system 2, and system 3 to see which email server or which server actually performs the best. And so there's a, if you go into the textbook, it'll explain what they're testing, but essentially we're testing 3 computer systems to see which one is better. Because we want to buy a new computer system, but these buggers are expensive. And so we have a policy at our company, if we're going to spend anything more than $20,000, we need to make sure that whatever it is that we're buying is going to improve the company. We just don't throw away money. Right? Anything over 20 grand, we want to make sure that it's worth buying. Right? Just not, okay, let's test it, and if we don't use it, cool. No. And so we want to test these 3 computers. So what am I going to do? I'm going to run an ANOVA, right? I want to test to see which one of these things are actually better. Can you guys see this? Shake your head, Lauren. Hannah, we good? You see it? Okay. I'm going to run a one-way ANOVA. I'm going to check these 3 computer servers against each other. Boom. I have to look in the book. I think it's 3.92. Enter. Okay. So when we look at this, we write our hypothesis here that system 1, system 2, and system 3 are all going to perform the same. They're going to upload these programs all the same. They're going to have the same refresh rate, but they're all going to perform the speed of a computer. And so some of you, like you have a computer, you turn it on and it takes forever. Like the speed of my computer stinks. Maybe some of you guys, your computers are much quicker. What they're doing is they're comparing the efficiency and the speed of the computer to see which one's the best fit. Right here, we're saying not all average speeds are the same. So not all the means are equal. One computer's better. So my level of significance was 0.05. My p-value is 0.015. So 0.01 is below 0.05. So there's significant evidence to reject the null, right? So evidence, oops. to reject the null if I am 99, oops, sorry, 99.4% confident that one of the computers or servers outperforms the rest. Okay. Which one outperforms the rest? We need to look at the Tukey-Kramer for that. So when we look at the Tukey-Kramer, right, we can actually make something known as a number line. So I'm going to look at which one produces the slowest. And so I look at our sample means over here. And the one that's the slowest is computer 3, followed by 2, followed by 1. So I make a number line from the lowest to the highest. 3, 2, 1. This is the lowest, and this is the highest performing. Now I'm going to use my Tukey-Kramer to see which one is statistically significantly different. Are 3 and 2, are they the same or different? So 3 and 2, if I go down here to the bottom where it says 2 and 3, means are not different. They're the same. Those aren't different. How about 2 and 1? Right? They're not different. How about 1 and 3? So 1 is statistically different than 3, but not than 2. So we'd say that 1 right here outperforms at least this one. So which one of these would we go with? Computing system 1, or server number 1. Okay. So the Tukey-Kramer tells us to go with server number 1, number uno. So now what we need to do, so our boss is going to say, so which one do you think we should go with? Well, so I looked at 3 different systems, and it's telling me that the Lenovo is probably the best. It seems like it outperforms the other ones significantly more. So I can say it significantly outperforms the rest of the other ones, right? It outperforms this one, but the other one is kind of the same, but it's much higher, but it outperforms the rest. The boss is like, okay, well, how do you know that your test is accurate, right? Because I know you're showing me the test. Okay, well, you know, what I did was I wanted to make sure that my test was accurate, so I checked it, right? And so this is how we make sure that our test is valid and reliable. P-value is still a little bit low, so if our skewness and kurtosis is off a little bit, we'd be okay. So do we see this for system 2? Our data is a little bit peaked and not normal. So here's a question. Blaze, are we there? Do we see this right here? So our p-value is below our level of significance. But when we look at our skewness and kurtosis, it tells us that our p-value is inaccurate. Does this kurtosis, even though it's not accurate, will we still be able to reject our null? So we have a kurtosis of 1.6. With this p-value, would you reject a null still or no? We know that that p-value is not accurate. Huh?
No.
You wouldn't reject it. Okay. How about you, Max? What are you thinking?
I would still reject it.
because we already know that with skewness and kurtosis, if it's only off by 1 or 2, that's less than 1%. You know, and so if it's off by less than 1%, our p-value is at 1. If it's off by 1%, even if it's at 2.5, it's still below, even adding the error of 1 in there, it's still below 0.5. So we'd still reject it. So in this case, it's still rejected. We'd still say we're going to go with server number 1. You'd still be able to say that. Okay? You with me so far? So now what we're going to do is we are going to introduce what the heck chi-square is. I don't think, say Thursday? Somebody give me a yes? Okay. So I'm going to introduce chi-square. And then on Monday, we will cover chi-square. So you can follow along if you want. I'm going to go to Excel note files. And after I go to Excel note files, I'm going to go to chapter 11. And I'm going to go to example like 11.3, 2 by 2, and 3 C tables. Oops. So let me now share my screen with you guys. Let's take a look at this. Nope. Not showing that. Hang on. I know that's the wrong one. I just want to choose. Here we go. Let's try this again. Okay. That's not working. Let's break this down old school. I've been doing this a while. So now let's so with chi-square, what we're looking at is we're trying to determine categorical data, and we're trying to add some attributes to that categorical data and see if there are reasons that certain things are taking place. Okay? So let me I'm going to break this down a little bit old school. Are we prepared for this? Yeah. Ready? Okay, so those of you that are still here, you're going to be blessed that you are. Okay, let's take a look and to see what this actually is and what's taking place with this chi-square. Okay, can you guys see me? Yes, no? Okay, so looking at this chi-square, what we can do, we can look at, here we have a bunch of different hotels. And we can look at what is the reason that they're staying at this hotel? Price, location, availability, other, or total. And so when we look at Hilton, we find out that 19 people stayed there because of the price. Ohana, 28. Holiday Inn, about 40. And are we out of time? One more minute. So for location, people stay at Hilton, 28. Ohana 9, Holiday Inn 5. Availability, Hilton 5, Ohana 15, Holiday Inn 13. Other, these are done. And so when we start looking at this, you can see what's important. Price. The people that stay at Holiday Inn, they're not price sensitive. Matter of fact, they want it to be more expensive. They want the price to be more expensive at the Holiday Inn. That way they tell their friends, where'd you stay? You stay at the Holiday Inn. The people at Ohana, they're a little bit price sensitive. The reason why they stay at Holiday Inn is they're very price sensitive. Hilton, it's the location. That's the location. Ohana, location, not really. Holiday Inn, no. Location is not even an issue. Availability, imagine you're coming out to Hawaii for the 4th of July. And you call them up, like right now, and say, hey, I'd like to come out there for the 4th of July. And they laugh. Are you kidding? You should have booked this a year ago. And then you tell your family, hey, family, well, you can't go out there the 4th of July, but we can get out there in August. And you take that appointment because you're willing to wait. You actually go and you look at availability for Ohana. Maybe you wait a little bit. Over here, Holiday Inn, you call them up. Hey, I'd like to get a room there for 4th of July. We don't have it. Okay. You actually don't wait. I guess we'll continue this on Monday. We're out of time. I see that we're now down to about half the class. Any of you that have questions, I just want to make sure that I started to cover it. That way, if you start homework, at least you'll have a sense of what's going on. So